Welcome to our discussion on doubling time and half-life. Let's start with some vocabulary. Doubling time is just the time it takes for anything to double. So to go from 4 organisms to 8 or 100 organisms to 200, it doesn't matter, just as long as it doubles, that's what we're looking for. And then of course, halving time, right, is the time it takes to cut something in half, go from 100 down to 50, then 50 down to 25, and so on and so forth. So after some time t, if we have an exponentially growing quantity with some known doubling time that we'll call it t sub double, just think of it as just 2, right, or 7, or 0.5, whatever it is, it's how long it takes for something to double. Then we know that this stuff, this quantity, whatever it is that's growing, will increase in size by a factor of 2 to the t divided by t double. So basically, it's doubling, right? So 2 to the t, where t is time. And as that time goes, it's being multiplied by a factor of 2. But since it takes, let's say, 5 seconds to double, then t would have to be 5, right, before it would double. And so if you set the t double to 5, so if here's our example. This might make more sense with some numbers. If, I'm going to call it TD for T double. If that is 5 seconds, then we know it's going to take exactly 5 seconds for something to double, right? So the time it takes for it to be multiplied by 2 is going to be 5. So when little t is 5 seconds, then we get 2 to the 5 over 5, right? Because this one here comes from TD, which ends up being just 2 to the 1, which of course is 2. So that's what we're basically getting at with this formula, is that if we know what the doubling time is, then the thing will increase in size by a factor of 2 to the power of little t over doubling time. Here's another example. So we know that some bank account takes 13 years to double. So what factor does it increase in 50 years? Well, if we just plug everything into the formula, it's just 2 to the 50 over 13, which is roughly 2 to the 3.8, blah, blah, blah. And when you put that in your calculator, it's about 14.382. So what that means is if you started off with $1,000 in this account in 50 years, it would be multiplied by 14.382, and you would have $14,382. That's all this whole factor thing means. Okay, there's a rule of 70, which is an approximate doubling time formula. And it basically says, so if you have any quantity that's growing exponentially and the exponential growth rate is p, we don't know what that is, but it has growth rate of 2% or 7% or 13%, whatever it is, that p, then the approximate doubling time is just 70 over that p. So we can use that to find the approximate growth rate, doubling time for something that's growing at 15%. And it would very easily, right, t double would just be 70 over that 15. And when you do the math, 4.6 repeating, or basically, 4.7, depending on where you want to round. Here's an example. If our world population doubled in the 40 years from 60 to 2000, we could actually figure out the approximate average percent growth rate during that period. And then we could compare that with the 2012 growth rate of 1.1% per year. Now, if we use the idea of, the approximate 70 over doubling time and plug in what we know that it took 40 years to double, so that goes into the bottom. 70 over 40 becomes 1.75 per year. And that's telling us that, remember, the answer is percentage, so that's a 1.75%. So according to the previous data, we were growing at roughly approximately 1.75% per year during that 4-year period. And if we're now growing at 1.1%, that means it's slower. That means it should take longer to double. Okay, exponential decay and half-life is really just something going in the opposite direction. So instead of something growing exponentially, it's decaying, getting smaller. So instead of a doubling time, you have a half-life time. So instead of being multiplied by a factor of 2, you're being multiplied by a factor of 1/2. And really all that's happening is you're just doing 1 over 2 to that power, and it becomes 1/2 to that same power. And instead of calling capital D the doubling time, we just call it the half-life time or half time. But it's all the same idea. So if we know radioactive carbon-14 has a half-life of about 5,700 years, and once something dies, it starts to decay, we can figure out what fraction of carbon-14 in an animal bone still remains 1,000 years after the animal has died, if we know how much carbon was in it, when it started. So the half-life, 5,700 years. So the fraction of the initial amount remaining after 1,000 years is very easily just 1/2 to the 1,000 over 5,700. You do the math and it comes out to about 0.885. So if the bone originally contained 1 kilogram of carbon-14, then after 1,000 years, it would have approximately 0.885 kilograms. And that's basically the technique they use for carbon dating things. They know how much carbon is in a particular organism. Then they can find, when they find a fossil of that organism and check its carbon levels, they use this to determine how old it is. Here's another example. Plutonium-239, 100 pounds of it, deposited in a nuclear waste site. How much of it will still be present in 100,000 years? If we know the half-life of plutonium is 24,000 years, well, 100,000 years is basically almost just a little over 4 of those, so it's going to be cut in half 4 times and then a little bit extra, right? But if you plug it into the actual formula, you can get the precise amount, which ends up being 5.6 pounds. Now, if you think about it, if you cut it in half, it goes down 50, right? That's one. Cut it in half again, 25. That's 2 cuts. Remember, we said it's going to be a little over 4. Cut it in half again, that's 12.5. Cut that in half, that's a little over 6. There's your 4 cuts, right? And then it's a little bit more. Remember, because if you divide 100,000 by 24, it's just a little bit more than 4 cuts, right? So that's how they get down to 5.6. Now, the approximate formula for half-life, you can see, is just the same as the approximate formula for doubling time, because we're basically doing the same thing. Right? Instead of multiplying by 2, you're multiplying by a half, which is really just 1 over 2 to that power. So of course the formula is exactly the same. Suppose that inflation causes the value of the Russian ruble to fall at a rate of 12% per year. At this rate, approximately how long does it take for the ruble to lose half of its value? Well, 70 over P, 70 over 12, it's going to take 5.8 years, or roughly 6 years if you round up. If we want to be more precise, we want to use exact formulas. So instead of, these approximations of 70 over something, we actually have perfect formulas that give us precise answers. And they're very easily just log base 10 of 2 over log base 10 of 1 plus r. And then the other one is log base 10 of 2 over log base 10 of 1 plus r. And you go, oh, wait a minute, that's the exact formula. Yes, of course it's the exact same formula. We just talked about this, right? That it's just the difference between doing 2 and then 1 over 2, so the formula is going to be the same. Now, you may have seen these formulas somewhere else written as just log of 2 over log of 1 plus r, and whenever you see log without anything, it's just assumed that it's base 10. But just so you know, and this is true for both of these formulas, you can do log of any base. So you could do log base 3 and log base 3, but that'd be kind of silly because most calculators can only do 2 logs, log base 10 and log base e, which is called the natural log. So really, the only other form of this formula that's readily used is natural log of 2 over natural log of 1 plus r. And that's actually the one that I like because I just like dealing with natural logs versus logs. But both formulas work. Here's an example using the formula. Population of rats growing at a rate of 80% per month. Find the exact doubling time for this growth rate. So we know all we have to do is plug everything in. So log base 10 of 2 over log base 10 of 1 plus r. And remember, r is our growth rate written as a decimal, so 80% becomes 0.8. And of course, we put that together, and 1 plus 0.8 just becomes 1.8. Take the log of the top, the log of the bottom, do the math, and it takes approximately 1.18 months. The only reason why that's a squiggly equals, it's not a precise answer, is because we rounded it to 2 decimals. But we did get a much more precise answer than doing 70 over 80. And in fact, if you do 70 over 80, you'll see that it's, quite different. Because remember, that was the approximate, 70 over p, and 70 over 80 is less than 1. And this is greater than 1. So you can see how that was an approximation, right? 0.875. So it's not too far off, but it's not great. It's much better to use the real formula. So let's start using the real formula, guys. And don't forget that this would have also worked had you done natural logs. So you could have done natural log of 2 over natural log of 1.8 and gotten the exact same answer. And that's everything you need to know for doubling and half-life.